Yeah, good afternoon, everyone. I hope you can see me. And hello, everyone. Good morning. And I can see the chat boxes today very clearly. Uh, I hope you had a good time yesterday with the workshop. I hope you learned quite a bit. So we missed one class, and it's okay. I mean, we will cover up for it in going forward. And yeah, so if you can hear me and if the sound and video and everything is good, just give me a confirmation on the chat boxes. I can see the chat box today clearly. I put it on my OBS desk doc as a doc, so it's easier for me. So now I can see all your comments. So if everything is good, just put in yeah. So I hope you were able to download Fusion 360 as well. Did you download Fusion 360? Did you look at the models? Just give me again. Yeah, just give me a shout for that. If you are facing some problems with Fusion 360 or I mean like learning and installation, I suggest you do try to sort it out very quickly, because yesterday's assignment, again, like we planned in the first class, it will have to be submitted by next week. Okay, so that is I think third, so maximum by third, so next Saturday you should be able to submit the assignment. So in this class also we so I do I have an assignment plan, but I have not put it over here. So what I will do is I will send you the assignment uh, in mail. Okay, and I will also put the assignment up on the OneNote file. Okay, so with that, let's start off with our presentation. Right. Good morning today, and we are going to take a look at um, uh, casting. Okay, so what we are specifically trying to look at, what kind of manufacturing processes are there when metal is in a molten state. Okay, so this chart that you see right now, Anushka is asking if I got my yeah, I got your mail and I got your assignment. I'll do that. Don't worry. Okay. Okay. So this chart that you see over here, that is a graphical representation of what we discussed earlier, of what happens at a micro scale when metal cools down from a liquid state to a solid state. Okay, so when metal is in a liquid state, there are these small areas where nucleation starts, where crystallization starts in the material, and you have some crystals forming, right? So in alloys, what happens is that each of these zones may have a slightly different composition of the percentage of different materials, of different elements that make up the alloy. Sometimes, let's say in steel, there may be 2 or 3 different types of these kind of crystal areas, and when they grow, they form these um, crystal structures wherein one space is different, one grain has a slightly different composition than the other, and so on. So like this it happens. Okay, so this is on the left hand side, you have the entirely liquid stage, okay, where the material is molten, and on the right hand side you have solid state. And as I said, we have manufacturing processes for each of these, let's say, 4 stages. So liquid stage, slightly semi-liquid, not semi-liquid but slightly plasticky shape, where the metal can still hold on to its shape, but it is very, very malleable in that sense. Okay, and finally at slightly heated temperature, when the metal is not very soft but still malleable, so that's called forming. And finally, at the solid stages, you can form the material, or you can also machine the materials. Okay, so these four different types of stages we can roughly say, where we can categorize different types of manufacturing process. So we'll take a look at casting, which is a category of manufacturing processes which use or manipulate liquid metal. Okay, so casting. So this chart is exactly what I was trying to explain you just before. So we have, in the liquid stage, we have casting. When it is slightly malleable, it is called forging, and that means you heat up the material to be softer in nature, and then you form it to a certain shape, okay, using any of the methods. Okay, like for example, just hammering, or let's say putting it into a die and pressing it together. So that's forging, right? And finally, in when the metal is in the solid stage also, you can actually do some forming operations. By forming, I mean you give the whole piece of the block of metal a certain shape by pressing it with enormous forces. Okay, so when the metal is perfectly solid, or in room temperature, or probably slightly elevated temperature, you can do these processes called shaping and drawing to form the metal into a certain shape. We will take a look at these two processes slightly later. Today we are going to concentrate on casting, because there are several types of casting processes, and the fundamentals are certainly the same, but there are several types, and we will look at the distinction between these different types, and hope you will appreciate these processes. Okay, before we dive into the whole process itself, let's first take a look at a few things, a few fundamentals of what happens when the metal cools down, because that becomes very, very essential for us. So what happens is, let's take this kind of an example. Okay, it's a it's a square column. So that means, imagine a rectangular prism of this kind of a cross section, or square cross section, and it's this tall, and imagine this is entirely filled up with molten material. Okay, so let's consider steel. Okay, most likely the graphic representation here, since there are different kind of colored grains here, white and gray, most likely this is a representation of steel. Okay, where these black grains and the white grains have slightly different compositions. Okay, so let's take a look at what happens when it cools down. So when it cools down, if let's say the temperature is if the temperature difference between the molten material and the environment in which this block is in, if that is quite high, that means the molten material can lose a lot of heat very quickly. Okay, what happens is that you will get this kind of a grain arrangement internally. So you will have the outer layer cool down very quickly. Okay, have you if you baked bread, or some kind of things in these kind of things in at your home, you will see what happens. So you have a loaf of bread, you have a bowl of dough, and you put it in the oven and you heat it up, and when it comes out of the oven, once you break it, what you see is the outer surface is harder, okay, and the inner surface is softer, right? So that kind of thing happens over here when it cools down. So here the outer layer, as you can see, has smaller grain structure, because that area was able to lose a lot of heat very fast to the environment. Okay, so you have smaller grain structures, as you go inside, this layer itself becomes like an insulation layer for the molten material that is now remaining on the inside of this block. Okay, so as you can see, smaller grain structures all around. And now these, imagine at a stage in time when it is cooling, this thing has solidified, so this becomes like an insulating layer for this molten material over here to lose heat to the outside. Okay, so if that temperature difference is very high, then despite this insulating layer of solidified material, the internal material will still lose a lot of heat very fast, and because of which these kind of columnar structures are formed, and the columnar structures kind of join together, kind of when they cool down, they form this kind of a shape it is observed. Okay, so they kind of join in some part and it forms this kind of thing. Now take a second scenario wherein the difference between the outer environment and the molten block, this block of material, is not so much. So let's say here, let's say it's steel and it's molten at 1400 degrees centigrade, and the outer temperature, let's say it's around 500 or 600 degrees centigrade, so it's very hot. Okay, so the amount of energy that can be released at this kind of a temperature difference is fairly lesser than, let's say, if we just leave it at room temperature. Correct? So here what happens is that you'll start seeing the same phenomenon. It will start in the same way. You'll have a smaller grain structure towards the outer surface where the metal is able to lose a lot of heat very quickly, and it will form this kind of a smaller grain, relatively smaller grain structure. However, from this case to this case, you will have slightly larger grains. Okay, because what happens is that the molten material, imagine in a even in a microscopic view, the crystals, since the molten material takes a bit of extra time to cool down, the crystals have a chance to grow a little larger, right? So because of which the grains themselves become slightly larger, right? So here the grains are slightly larger than case 1, case A, but they still form this kind of a smaller grain structure compared to other internal grains that will be formed in this, and it forms an internal layer of insulation for the material. Okay, and the same thing happens. You start these columnar structures start forming, and at some point of time what happens is that this outer layer forms like a very thick insulating layer, and the amount of heat that can be released by the central molten column, in this case, in the second case, to the outer environment, that means the amount of energy that this can lose to the environment becomes very less. Okay, so the what we say is the temperature gradation, okay, becomes quite less, and because of which fairly large and homogeneous grain structures are formed. Okay, as you can see in this cross section, this small section at the center has larger grain structures, and that can be seen in this cross section area also. So these two kind of give you an idea of if we have a material which is casted, when it is cooled down, what is the arrangement of grains internally, and this becomes very important for us to know about the strength of that casted part. Okay, and this is one of the things that you need to control when you are designing for casting. Okay, now it is possible to make this block entirely into this kind of larger and homogeneous grain structures. This is called the equiaxed zone here. Okay, so where the grain structure is homogeneous in sizes, and it is fairly larger than the other sizes. So these other sections are called the chill zone and the columnar zone of grains. And it is possible to have the entire structure in an equiaxed form, and this is more desired because, as you can imagine, because of the nature of the uniformity of the grain sizes, the whole piece will have a fairly uniform mechanical property, okay, across its dimensions. Okay, so that means this part will not behave anistropically. Anistropicity is the property of let's say a part of material where the mechanical properties are different in different dimensions. Okay, so on, let's say, axially, it is slightly more stronger. Let me just change my video to the right so that you can see, right? So so you can you have, like, let's say a solid piece of bar. If it is stronger, let's say tensile strength is stronger on one side than the other side, then the material is behaving anistropically. So for an equiaxed structure, grain structure piece, the mechanical properties are fairly uniform and the material does not behave anistropically. Okay, sometimes you would want some parts to behave anistropically, sometimes you wouldn't. Okay, that will depend on the nature of the requirement. Okay, so let's move on. And the same thing what I had explained, this kind of chart gives you an idea of how such an equiaxed structure is formed internally. So on the bottom side, this shows how the at, let's say, at 8 minutes temperature or 40 minutes, what kind of things are seen. And so this gives you an idea of how quickly the grains are forming. So as you can see from, let's say, the first 3 images, the initial dendritic and the columnar structure of grains forms very quickly, whereas as you go forward, the amount of time taken for the material to cool down is much longer, right? So 40 to 100 minutes over here, and here it was in just 40 minutes or something like that. Okay, so let's take a look at casting. So casting is I'm sure you know this, like, so basically the idea is that you create a cavity, a space which does not have anything inside some other space, right? So here in this image, what you see is, you see this part, you see this is sand. Okay, so sand, the reason they use sand is because the temperature at which sand becomes glass is much higher than the molten temperature of the material. Okay, so here inside this block of wood and sand, there is a cavity, there is a space where the material can flow and take that shape. And once the metal is poured and it cools down, that whole sand is removed and you get the cavity. Okay, so it's very difficult to explain it just through images. So what I have tried to do is, I've tried to put in some videos. We'll come to this video slightly later. Let's first take a look at like an industrial scale casting. Okay, let's say you want to cast like a large motor's impeller blades, the blades that not motor, large pumps impeller blade or something like that. Okay, then let's take a look at this video. I've got this from the internet, and
VoxelJet offers the
can you
manufacture of complex molds using 3D print.
The core of
just
a
tell
wheel
me if you
and
can
its
hear the
underparts
sound
can
clearly. Okay,
now be easily produced in one piece. On request, we can take over the production of the sand mold design based on your 3D data. Depending on the application, prototypes and small series can easily be produced in various sand types. The recoater applies sand to the 4-meter long build space in one layer. At the same time, the printhead starts to selectively dose the resin where the mold will be created. This layer building method allows for the production of complex geometries with undercuts in one piece. After the build process is
So as you can see, this is like a very large scale 3D printing setup where instead of printing with plastic, they are printing with sand. And what I'm showing you is a slightly advanced version of the casting process. Okay, it's a much advanced version of the casting process, not just because of the use of 3D printing, but also in typical processes you don't use something called a core. So here we are using something called a core. I'll explain you what a core is in going forward, but let's first take a look at this video to understand the whole process. Okay,
complete, the mold can be easily unpacked. The handling of the molds in the foundry is the same as with conventional production method. The unbound sand can be easily removed and the molds are ready for immediate casting. Because of the different delivery periods, you can coordinate the molds to your production. The voxeljet 3D printing process allows for the cost-effective and time-saving manufacture of your components with a high degree of precision.
so somebody else
The Wolfensberger Steel Foundry and Voxeljet manufacture a complex wheel using a combination of traditional mold construction and modern 3D printing. The external shape of the prototype is made in a conventional manner, using existing models. No models are built for the core. It is delivered by Voxeljet on a just-in-time basis and is then integrated and processed in line with the normal work process. Assembly involves just one core rather than multiple core segments. The client can choose from suitable sand varieties for the various cast alloys. The cast features the typical foundry properties and can be optimized through the use of cores printed with the 3D method. The cast can be removed from the mold in the usual manner. A smaller number of core flashes and an excellent surface make for quick and cost-effective cleaning of cast parts. The cast part then undergoes the usual quality checks, such as X-rays, color penetration testing, or ultrasound. The result is a complex wheel that impresses with its component accuracy and consistency in form. Are you interested? We would be pleased to assist you.
It was quite complicated, and I'm sure many of you did not follow what happened over here. Okay. Okay, I hope this is better. Manu, I hope this is better. I hope you can hear me now. Okay. Right. So what I was saying is, if you saw the video, I'm sure many of you are totally confused. What on earth is happening over here? Okay. They just 3D printed something, put it on something, and hello. Now tell me if you can hear me. Yeah. Okay. Okay. Yeah. I think I kind of changed the settings here and there a little bit. Anyway. Okay. So I hope the voice is better now. So I was saying it must have been difficult for you to understand this because it is a fairly advanced video that I showed you. It's a really complicated, process at what they are doing, and it is an advanced manufacturing process. So let's take a look at this in a very simple form. Let's say if you want to do casting at home, okay, how would you do? I mean, I don't suggest you do unless you have the proper knowledge, but let's say if you did want to do it, then how would you do it? Okay, so let's take a look at that. So now I can kind of go into the previous videos. So first, before starting the process, casting process, you need to make something with which you will be able to make a cavity. Okay, so you have a sand, you have a space. Let's say you want to make a cavity in sand using something, so that's something you need to make. and that something is called the pattern. So first you need to make like a master. So what exactly will be the final casted product that you need to make using any kind of materials. Sometimes you make it out of wood, sometimes you make it out of plastic, some you can even 3D print it nowadays, or whatever. So whatever is possible, or you can just hack and slash and glue together things to get a certain shape, and that is your master. So let's say I want to cast, let me take a prop. So let's say, give me a second, I don't have a prop. Okay, let's say I want to cast this piece. Okay, this is like a what is this? It's a power bank. Okay, so let's say I want to make a casted piece just like this shape. Okay, right. So if I want to make a cast of this, what I want to do, I'll make this piece. If I want to make this piece out of casted metal, I'll make this exact same thing in plastic or in wood, and that will be my master. Okay, and when I make the whole sand bay, the part with the sand ready for casting, I'll use this to make an impression in the sand, and that impression, when I remove this, that impression is where I will fill the metal. Okay, so I explained it to you without trying to use any jargon, but all of these terms, all of these things have certain terminologies associated, and you need to know those terminologies. So let's take a look at the video now and appreciate how it's done. So this guy is trying to make a slingshot. Okay, so I'll just first increase the desktop audio, and let's see if you can hear it. So what? Okay.
I begin with 2 pieces of wood, which I stick together with a glue stick and a single sheet of newspaper between them. Then I had to take some material off to give it the appropriate dimensions for the pattern.
So remember, he's trying to make just the pattern. Okay, and
wood, which I Then I had to take some material off to give it the appropriate dimensions for the pattern. I traced the outlines of the slingshot onto the piece. There is a link in the description of my Lost Foam slingshot casting video where you can get the templates for free. Then cutting it out on the bandsaw.
So the reason he has he has a piece of paper stuck in between these two wooden pieces is because after making the whole pattern, he wants to remove these two pieces and have like the pattern made in 2 pieces. Okay, you will understand the reason slightly why.
I glued the block back together with glue stick, and because this didn't work at all, I used some yellow tape to hold it together. At this point I realized I had forgotten to drill the alignment pin holes.
Okay, so
now
he's
rounding and
just
sculpting the
finishing
blank.
all of this. And most of these tools are available in the
smoothing it with
department.
the
So
homemade
once you
flap
come back,
sander.
if any of you are
I
actually
separated
interested in
the 2
making
halves
it,
using an X-Acto knife. A little piece broke off, but I could easily glue it back on.
so that's the reason he had like piece of paper stuck in the middle, because he
I
wanted
glued
to
in some
divide it
dowels
into
for
pieces.
the alignment pins and covered the slingshot in wood filler.
Okay. Now in making patterns for casting, it's very important to have the pattern, okay, the master, this pattern as in a very good surface finish. Okay, surface finish has to be really excellent. Why? Because first and foremost, the surface finish of the pattern reflects on the surface finish of the casting. If the surface finish is not very good, of the pattern is not very good, the casting surface finish will also be not very good. The other thing is, if the surface finish is not very good, for pattern surface finish is not very good, you will find it difficult to remove it from the casting, from the mold. Okay,
then I sanded it nice and smooth.
so if you notice carefully, he has these holes which are there for purposes of alignment and all of these reasons. Okay,
I spray painted it and smoothened it. I repeated this process several times.
so this kind of spray painting gives the really good surface finish, right? So yeah, so that is just the making of the pattern. Okay, once this pattern is ready, you can go to casting. Okay, right, so let's take a look at casting. And first of all, sound and all is okay, right? Okay, so let's take a look at casting this. You will see he tries to make all of this.
I made this pattern in one of my other videos. The link will be in the description. There will also be a link to a video where I show how to cast the aluminium slingshot without the need for woodworking equipment for making the pattern. Need for woodworking equipment,
so
the aluminium. There will
small
also be a
wooden
link
piece.
to a video
Okay.
where I show how.
So notice this carefully. So here you on the I think your right hand side you will have like a this is the sand, okay, and the sand has certain texture to it. So by the look of it, had you been here, I would have actually shown you that this is what the sand feels like and so on. But I think here now you can only see it visually, right? So the sand is not entirely dry, so it is slightly wet. So generally in green sand casting, there is sand and there is some form of a binding agent mixed with sand at a certain ratio. Okay, and Devaditya, don't worry, welcome. Okay, so what the property of this is that, so there's a very nice thumb rule to check if the sand is good for casting. So what you do is you take the sand in your hand and you clench your fist and you open your fist. The piece of sand should be just retain its shape. Okay, and if you just tap it slightly, it should break. So that is the consistency that you want. It's not too wet, not too dry. If the sand is too wet, imagine what will happen. When you pour metal, the water in the sand will evaporate and these water vapor will bubble into the molten metal. Okay, and you will get these small bubbles internally. So that is one of the casting defects. We will talk about this later. So the second part that I want to tell you here is this structure. Okay, this is a wooden structure. In his case, a wooden structure. It can be made out of any material. But this structure will hold the sand. So you will put the sand into this structure and you will press it in. Okay, and it has two parts, the top part and the bottom part. The bottom part is called the drag. Okay, you can and the top part is called the cope, COPE, and the bottom part is called the drag. you can kind of remember it like this, like the part that is on the ground and which will be dragged is the drag. Okay, so that's a so as you can see, he has these uh, you know structures on the side which ensure that the box fits exactly the same way every time. Okay, because slight bit of misalignment in the orientation of these boxes will also create some defects in the casting.
How to cast the aluminium slingshot without the need for woodworking equipment for making the pattern.
Okay, so now
I got the molding sand off eBay. It is not
think about what he did. He turned it over, and the reason he turned it over was he wants the cavity, the gap in which the metal will fill in between these two boxes, the place where these two boxes join. That is the point where he wants the cavity. Okay,
expensive. To make the mold, one half of the pattern is laid face down into the flask. I apply a bit of talcum powder to prevent the pattern from sticking to the mold. Then the flask is completely packed with sand.
So a little bit of powder kind of works like a lubricating agent, and it does not, it helps the sand from not entirely sticking onto the pattern. So as you can see, he's packing it with quite a bit of force.
And the excess is then scraped away.
Now when he turns it over, this is what happens. And now he can just remove this piece and
I had
he
to
will get
repair
the
the
gap.
areas around the fork tips because the pattern had moved slightly.
Since it's a DIY method, so he will obviously do a lot of things slightly jugaad. Typically it's not done in production, but this is a very good explanation video to understand casting. Okay, so consider it that way. So the coke is now put on top.
Now the second half of the mold can be made in similar fashion, only that I added a silicone cartridge to form the sprue for pouring in the molten metal.
So here, what he's done is he's going to put this silicone cartridge. So don't consider it as a silicone cartridge. The silicone makes no sense here. But the idea is that he's putting like a cylindrical piece there. Okay. Now when he packs in the material, that space also no sand will go in, and because of that this space will become available for him to pour the molten material. So that's the idea. Yeah, so Manu's question is, can you reuse the sand? Yes, you can reuse the sand after you've done casting. So there will be some amount of sand which gets burnt out, but besides that, you
now the mold
reuse.
can be opened and the pattern can be removed.
So now when he opens, you have one half of the pattern stuck on one side and the other half of the pattern stuck on the other side. Okay.
Vent holes are poked at the high spots of the cavity for the air to escape out of the mold.
So this is very important, right? So when you close these two pieces together, there is some air that is there inside. Okay, when you pour in material, that air needs some place to go. If you've not thought about that, what will happen is that you can imagine it's something like a cup being dipped into water, right? Inverted cup dipped into water. So the air inside the cup kind of stays inside. So something similar happens. If you don't have space for the air to escape at the right places, then when you pour the material, it'll the air will get collected into some spaces and it will create problems in the casting. Okay, so yeah, so these are the vent holes that he's creating, and he's creating it at places where it is the highest, the highest locations where the air might get.
A tunnel is created to connect the sprue to the cavity.
Now this small area that he's creating is for the metal to flow into the cavity, and this is called the gate. Okay, GATE, gate.
The mold is closed and now ready for pouring.
And now he will carefully place it. So naturally you can see, since it's sand, it's open from the both the sides, it needs to be handled really carefully. Slightly moving it in the with the wrong force or slight amount of extra vibrations will destroy this amount of. So he's melting aluminium.
Aluminium was molten in a coal fire and then poured into the mold.
With steel also.
Clamps guaranteed the mold won't open and let the aluminium spill out.
So remember, this is also one of the very important steps in casting, to ensure that the cope and drag are clamped together very, very tightly, or quite tightly, enough that the molten material, once it's poured down, it doesn't flow out of these gaps between the cope and the drag. Okay, if it flows out, then what you get is something called flash. Okay, and I can show you flash generally in plastic parts. No, if you observe in cheaper plastic parts, let's say, if you observe carefully, especially in cheap toys and all, there's a line somewhere in the middle and some amount of plastic kind of comes out. Okay, so that piece is where the two halves of the injection mold has met, and the plastic, instead of just filling the cavity, it has also come out of these gaps between the two halves of the mold. Okay, and that part is called the flash. So this kind of a tightening of the cope and drag with the clamps in this case, there are many other ways to do it. So this kind of tightening ensures that the molten material doesn't flow out of the gaps between the cope and the drag. Okay. So when you heat material, when you melt material, whatever impurities are there in the material, there's always some kind of impurities that kind of come to the top in the form of foam. Okay, so it's something like, so if you made dal at home, no, so once you heat it, so once the whole thing comes to a boil, you'll get a foam on top. No, something similar happens when you melt material. So that needs to be removed, and just the molten part needs to be poured. Okay, so that he's removing over here. That molten part is called slag, SLAG. So aluminium doesn't look red hot when it's molten. So he stops when it comes to the top over here, and based on this he is kind of very sure that internally the whole cavity is totally filled up. Okay, if he did not have this kind of an indication to know whether the internal cavity is filled up or not, it will be very difficult to ensure something like that. So now that's done, and this is what comes out. So as you can see, the sand around the whole thing is burnt. Okay, so it's blackened, and in fact to a certain degree it's burnt. Okay, and in fact the sand to the other side, to the other, in the other areas also have kind of dried out because of the heat of the metal. Okay, so yeah, and the surfaces, you can see the kind of surface finish that is achieved. So it's slightly pitted because of the texture of the sand itself. Okay.
I was really surprised how well it turned out. The surface of the casting is really nice, almost acceptable for a slingshot. The molding sand can be reused several times.
So it's not a good idea to reuse the burnt sand, but yeah, I mean, since it's a very DIY kind of situation, then it's okay, right? Now the gate and the pouring place, okay, I'll call it pouring place right now, that is chopped off, and this is what you get. And you can see the small blemishes that are there. So these small blemishes that are there, so those are they may have been created by either because of the sand kind of falling into that place, or let's say there's some amount of excess water vapor in there which kind of became trapped in the sand, or air or water vapor. You see these small areas, and this line is the line where the cope and the drag met, and this is called the parting line. In every plastic product which is injection molded, you will definitely see this line. Okay, and every part which is casted, unless it's totally finished and all, you can see this line. Okay, so yeah, so let's go back 2 minutes. Yeah. Oh shit. So look at this place here. So this is a small defect that is there in the casting. I mean, it's nothing. It's not a like a defect that will hinder him from using this part, but this just to explain it to you. So this is the place where there was some small gap that remained between the cope and drag when they met, and the metal kind of flowed into that space, and this is called the flash. Okay. Now it's just a matter of finishing it with whatever tools and whatever methods that you have, and in this case he is using an angle grinder. You can take it to other processes. Now once this block is done, you can do machining, you can do sanding, you can drill necessary holes that are needed and connect it to other pieces and so on. Okay, in this case it's just making a slingshot.
If I had a buffing wheel, I could polish this up to mirror finish, but I really didn't want to take the time to do it by hand. So that's what it is. I hope you liked it.
Okay. I thought it was an excellent project, and yeah, so it really tells you about the fundamentals, the simple basic fundamentals of casting, and beyond this, it's just improving the process. Okay, so beyond this, okay, so that's the pattern, and this is the casted, and now you can reuse the pattern to make other castings and so on and so forth. Okay, right. So now if you recall the first video that we saw, in that the pattern was made out of casting, okay, and additive manufacturing, and then that was used in like an industrial scale cope and drag which is made out of metal, and the packing of the sand was also done by a machine. Okay, so now let's just take a look at that video again, or you can go back and see that video later on in the this thing. Let's move forward. So now let's come to the actual technical jargons of the whole thing, and this image is like the cavity, is just the cavity. What is there inside the cope and drag. Okay, once you pour the metal, what comes out? Okay, what's the piece that comes out? That is this image. Okay, and here you can see what are the terminologies used. So the gray part is the casting, right? This is the piece that we want, and the line in the center is the parting line. Okay, and so here in this case, the casting is arranged in such a way that you pour here at this end, the metal travels through and comes out of this. So these surfaces, 1, 2, 3 surfaces are exposed to the top. Okay. So for the metal to go through, there are some other stages through which it goes. Okay. So first is this pouring cup. There's a small area which is created which makes it easy for the manufacturer to pour molten material in this space, and the design can vary slightly also, and this is called the pouring cup. So metal is poured over here, it comes down, and this place where it kind of comes down, it swirls a little bit and it comes down, it loses its turbulence a little bit, and it's called a sprue. Okay, the one that connects it to a runner. A runner is a space which is created so that the flow in the metal is made more uniform. Okay, so the molten material flows more uniformly. Okay, now after that, the runner, there's a small space that is created here. So all of this is optional. Okay, this green thing is kind of optional. It depends on what the shape that you are trying to cast. And so the idea is that molten material comes in and it starts filling in both these places together. So it fills up here, it fills up here, and at some point, once the whole space is filled up, Demon Gaming, I again forget. So what kind of issues are you facing? Is anybody else facing any issues? I mean, in hearing me or seeing the slides or something? So just tell me in the comment box. I think one of you is facing an issue. Okay. Any case, I mean, even if you're facing connectivity issue, try to stay in the stream, and once it's done, you can kind of go back and look at the whole thing. Okay. Yeah. Okay, maybe it's because it's raining or something like that. Anyway, okay, so let's go forward. So what you can see, as I was saying, once the material is poured in, it fills in and it reaches the top. Okay, so it reaches the top of these two places, and now you can kind of be sure that the whole cavity is totally filled up. What happens when the metal is cooled down? When it's cooled down, when it cools down, it shrinks, right? It shrinks in volume. Okay, and when it shrinks in volume, it'll try to pull in material from any place which is there. Okay, and this riser, the side riser and the top riser, are two places which work like reservoirs of molten material. And when the main casting body, which is the largest volume in the whole piece, it tries to cool down, it pulls in material from these two spaces, and that ensures that the casting dimension is not warped, it's not it's not changed, and it comes out fairly close to the dimensions that we want. Okay, so these are some of the terminologies here, like things you should know. Pattern, what is a pattern, what is a mold, what is the core. Okay, core we'll talk, cope and drag. Right, okay. So now one of the main problems, I don't know if you can see the problem, but how do you create something which has an internal hole in it. Okay, so let's say a kind of a pipe. Okay, so let's say this part itself, so this drawing, okay, this is a drawing of a part, and what the dotted lines show is that internally this part is hollow. Okay, so you have this kind of a right angle turn, but internally it is connected. So how do you get this? So the way to get this is using something called a core. Okay, a core is another piece of metal, material, not metal, which is made out of a slightly more stronger, I shouldn't say stronger, but more binded piece of sand in terms of sand casting. And that piece, once a pattern is created, let's say the slingshot had a hole in the center. Okay, so once the pattern is created, you remove the core and the cope and the drag, and in the cavity that is created, you put this core. Okay, this is also made out of sand. Okay, you put this core and you close the cope and the drag. Now wherever that core is there, that place the metal won't fill up, and that place you will get like a cavity. You will not get molten metal filled up, and that will create the hole that is needed. So here in this series of images, that kind of casting which uses a core is shown. Okay, so the first is the mechanical drawing. The second thing is we start with making the core. Okay, so the core is this internal shape, the internal holes that is needed, and they would print like the same way you would make like two pieces of the core, and whatever gate and riser and racks, all of these things are needed. You would make those pieces, and you make these kind of core boxes, something similar, right? So you do one step of casting first before you do the main casting. Okay, you make these core boxes using these core patterns, right? I don't get. Ace asks, okay, Sachin is saying when I play the video, the audio of the video is louder than your voice. I hope you can, I tried to pause. I mean, I hope you can kind of go back and see. Okay. Ace, I don't get this part. Won't the core touch the base and then ruin the structure? We'll see. Okay. So maybe once this whole thing is done. So let's first make just this internal cavity part. Okay. So we made these two boxes, and on that, let's say we joined these two boxes and made this small core. Okay, so this represents the hole that needs to be there within the part. Okay, and after that we make the pattern of the part in a solid form without the internal holes. Okay, and use that to create the casting pattern. So here I'm putting the pattern of this thing. I'm putting the screws and the risers and all of these things necessary, and packing it up with the sand and turn it around, and I have this, right? So it's not very clear in this, but the idea is that once that pattern is created, I will place the core in between inside this pattern. Okay, so I made the slingshot pattern exactly as it is, and to the point where it is divided just like this, and now in that I place this. Okay, this small thing I place inside that cavity which is of the pipe which is created, and now when I close it, okay, I am sure that the places where that core was there would not have been there, the molten material would not travel there. And now when I close it and I tighten it and I fill it, what happens is that all these places where there was these sprues and risers and all that, I'll get the molten material, but internally that thing, that core, because of the core, the material did not fill in. remember the core is also made out of sand, so it needs to be broken and removed, okay, but it is a slightly more binded and stronger piece of sand, okay. uh, so the core is extended so that it is longer than the pattern asks Gaurav, and it's right, okay. So the core is extended just to ensure that, so if the core was till here only, till at this point, this part would get closed down. So the core is slightly extended, and when you would make the pattern for this part, you would make it exactly to this dimension, but the core you would extend it just slightly, and you would ensure that there's just enough space for the core to fit in, and you would fit in into that place, okay. So we'll see that in another diagram. Let's hope that becomes clearer once that. So you understand the requirement for the core, okay. And yeah, we'll come back to this one slightly later, okay. So let's take a look at this. So this is what we are trying to create. We are trying to create this kind of a part, okay, and we want a hole here, and what we created was a pattern which is of this shape, from here to here, 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 right. So this kind of pattern we created, okay. Let me, I have this thing, I have right. So let me just tell you. So the pattern that I created was something like this, okay. Okay, if I see it, maybe it's in 3-dimension, it's something like this. Okay, this is the piece of wood that I created, and then I made the cope and drag impression using this part. Now I had a second piece which is the core, which is of this shape, and I placed it in this position after the cavity was created. Now in this case, what is happening is that since the core is kind of quite extended towards the internal part, I think that when I pour the metal, because of the forces of the pouring and because of the cooling and the shrinkage forces, it might break, okay. So I put these kind of 2 metal pins of probably the similar kind of composition as the base material, okay, and these are called chaplets, and when I cast the material, these will get absorbed into the casting, okay. So these, when it is not casted, when I am creating the cavity, these help in kind of holding up the core in the right place, okay. So right, so this is the kind of thing that is created. So once so that is just the core and the cavity, but to have the whole casting process properly done, you need to have these kind of other things, right. So first and foremost, I need like vents from where the air can escape. So let's say this is first and foremost, I want to have a pouring basin, so I'll start pouring here, and so the material, you can imagine what will happen. So it will go in like this, right. So it will splash, right. So that splashing, so I don't want that splashing to ruin the cope and drag sand casting. So because of that, I need this kind of a shape, and after that the material kind of flows in internally. It goes in, and once it's gets stuck, comes down here, there's like a small area which creates, which breaks the turbulence of the molten material, right. So the material is coming down like this, and it there's some amount of turbulence that kind of gets equalized and it starts filling in and it pours down and it starts filling it properly. Right? And all the air that is there, it kind of escapes over here and it fills up to this position. The metal also fills up to this position. So that's how the whole thing works. Now when it is done, I'll get this piece with this whole piece where I marked red. I'll get that as the final casting for me. Okay, right. Okay, so these are the chaplets which I was talking to you about. These are typically made with the same kind of materials with which you are going to cast. Okay, how is the blind riser made? So when you are trying to make the cope, right, so it's inverted, no, it's very easy to make that kind of a shape now. So when it is inverted, you just place something over there with the pattern and remove it, right? So it's okay, yeah. So here you can see what's the cores, what the cores look like. So this one of them, this one, the one that is generally coated with the agent to help you remove the cope and drag pattern. This blue agent in this case is the drag typically. Okay, and this one over here is the cope. Okay, and here they've just shown you by placing the cope in the right place, in the core in the cope, but rather it should be placed here. Okay, and then this is closed. So the idea is that these are all the cavities that's there, and here in this case you can see the casting. You are trying to make 4 different pieces of casting. This is a fairly complicated type where you have to be really aware of how the material flows in all of these uniformly. Okay, so this probably is the place where it will be. Okay, I'm sorry, I think this is the cope, this is not the drag. So this is the drag, but I'm not sure why this is painted and this is not, but okay. So this will be put on top, and this drag, you see these 3 cavities are the different parts that are created. 1, 2, 3, 4, these different parts. Okay, and this piece is the core. So now once I place the core, once I fit this in, what will happen is that I'll get a piece which has a central hole in there. Okay, I hope you understand. Okay, so this is what the whole sand casting arrangement looks like. And now right. So one of the main things to consider is that metals shrink considerably when they are cooling down. Okay, especially when they are cooling down from molten to a solid state, there is a significant amount of shrinkage in volume. Okay, and this kind of gives you an idea. Aluminium kind of shrinks around 6%. So you have to when you are making the patterns for casting, no, you have to consider this. So you have to design the pattern actually slightly larger, around 6.6% larger in volume than what you expect to get. Okay, so similarly all these are there, and as you can see, carbon steel around 2 to 3% is the volumetric reduction and so on. Okay, the other thing that you have to understand, that the shrinkage is not uniform. It's not like it's shrunk in a software, right? It's not like a scale operation in a software. So rather the shrinkage happens non-uniformly based on the thermal mass that is there. So in this case, no, this is small diagrammatic representation of what exactly happens. So let's say when we have poured into the material, let's say it's a cylinder, and we've poured in the molten material in this way, and so there are different types of shrinkages which happens. So first one is the liquid shrinkage, because once the liquid is poured in and the molten material comes from the temperature it is at to the melting point, right, to that kind of space. So the whole thing shrinks uniformly. Okay, once the melting point is hit and the metal starts solidifying, then what happens is that, as we discussed earlier, the parts that are closest to the atmosphere loses heat much faster, and hence cools down and hence solidifies. Okay, and this part gets solidified early, and as you can see, as it goes to the center, the solidification of it becomes, gets slower. And when the reason that this kind of shrinkage pattern happens is because when this part is shrinking, when the outer layer is shrinking, it's kind of pulling in material from the other side so that it does not change in dimension, and because of that you will get these kind of material will reduce from the center, and hence you will get this kind of a shape. Okay, so this is solidification shrinkage. So here the thing that will reduce this kind of a error, this kind of a shrinkage, or make it more uniform, rather, it's not possible to eliminate it. So the way to make it more uniform in shrinkage is by designing the gating and the rising pattern properly. And finally, once the whole thing is fully solidified, the metal is still hot, and by the time it comes down to room temperature, that solid itself shrinks, and that is also like a fairly uniform kind of shrinkage. Okay, so this is how the shrinkage happens. And typically on this side you are seeing like the kind of allowances that you should keep. So for aluminum alloys, you should always think about some 1.3% shrinkage allowance you should add. Okay, right. And besides that, the second thing that is most important, so here we did not even talk about it right now, but we will talk about it. Let's take a look at this one. So imagine this is the thing that we want to cast. Okay, we want to cast a piece which is of the shape T, and it has a small thing which is extending out, and this is naturally the drag, and it has all straight edges. So once I press the pattern in the mold, when I try to remove it, it will be very difficult to remove it, because all of these flat surfaces will have a tremendous amount of friction which will damage the cope. Okay, damage the sand in the cope. And to avoid this, what you do is you add some small angle to all the horizontal surfaces. Now you have to think about the model from the perspective of a parting line and cope and drag. So which part goes into cope, which part goes into drag, right? So based on that parting line, you have to think about this something called draft angle. You have to place a little bit of angle in all the flat surfaces. The angle is from the vertical, and this angle, what it does is, once you try to remove it, it will just pop out a little bit and you will get this smoother finish. Okay, so this is called draft angle, and it is one of the most important concepts in casting, injection molding, and all of these manufacturing processes where a die is involved. Okay, when there is a die which has two parts and you have material which needs to be pressed in, you need to consider something called draft angle. We'll come to all of these slides, are very interesting slides. Right, so in this image, what it's showing you is what are the allowances that you will need to keep for a certain design. So let's say the gray part is the shaded part is the part that you want. Okay. You see this small notch. Now imagine a pattern. So imagine something like this. You want to create it in directly in this pattern. Okay. So this notch will not be possible without doing some major, critical changes to the casting setup. Okay. So this kind of a thing is called an undercut, under CUT. Okay. So the reason this is not possible is, imagine the parting line to be here. Okay. So at this top surface, or let's say the parting line is somewhere in the middle. Okay. So this part goes into the cope, this part goes into the drag, and the parting line is somewhere in the middle. Okay. So imagine the sand will kind of flow into this, and you will not be able to remove this part, right? So remove this pattern from the sand. So so what you would typically do is, such kind of undercuts areas, either you use a core or something like that, or you keep it for machining later on. So in this case, this V slot is kept for machining later on. So this is the part that you want. You remove this thinking that you will machine it. Now you will add probably 3 mm all around for cleanup. So if you want this to be perfectly machined surface, then around 3 mm is like a thumb rule. Okay, it depends on what kind of what kind of casting process you are using. But think about in sand casting only. So in sand casting, if you want to have a flat surface, smooth finished flat surface, you need to at least keep 3 mm so that you can machine that surface and make it flat. Okay, and grind it and so on. So 3 mm of allowances all around. And next is the draft angle. Okay, so you add the draft angle to all the flat surfaces. So now this, let's say I said the parting line is somewhere here, and this is straight. Okay, perpendicular to the parting line. So that is not acceptable. So any surfaces which are perpendicular to the parting line, you add around 1.5 degrees of allowances. 1.5 degrees is actually quite less. It's okay. 1.5 degrees is okay, but a good sand casting setup, especially a sand casting setup, around 3 mm to 5 mm is what is sought after. Especially if it is a very flat and very long surface, perpendicular surface, typically you should go for something around 3.5, 4 mm, 4 degrees of draft angle. Okay, so these are like thumb rules, and it's come from kind of experience of the manufacturers. Okay, right. So let's go forward, and I want to introduce you to the various defects that are there in casting. So sand casting was the fundamental of all. Sand casting kind of explains the fundamentals of all types of casting processes, and the defects are kind of similar. The allowances are kind of similar when you are considering all different types of manufacturing process. So let's take a look at these. Right. So when you cast metal, there are some internal forces at play, and the most of these internal forces come into play because of the shrinkage of the part itself. Okay, and when the material shrinks, so most designs are like not flat, straightforward, like, so they are slightly complicated. There are slightly larger volumes in some places, there are smaller volumes in some places, there are some features which are extruding out of the surfaces of the part. So because of these changes in dimensions, okay, changes in form, there are some places which there is more stresses because of thermal expansion and contraction of the material. Okay? So in this case, so things like hot tears are created because of something like this. Generally, this happens when there are two surfaces which are at a sharp angle to each other. So let's say in this case, this and this are at a sharp angle. This does not happen because of sand flowing into the cavity. This happens because the material, when it cools down, it does not get enough supply of molten material to retain its dimension, so it tears from some places. Okay, and so all these spaces are hot tears. Okay, and in cylindrical cavities what happens is, so think about this. Okay, so you poured the material, it went in, it flowed from the top to bottom, and when it cooled down, so what happened was it probably started cooling, let's say at one end, at this end it started cooling. Okay, and when it started cooling, no, you can, if you think about the outer layer of the whole thing, it kind of gets pulled to a certain direction, to the direction which is getting cooled faster. And when this kind of pulling forces come into play, you'll get some spaces which get tears. So the main reason for hot tears are because of non-uniform cooling of the surfaces of the casting. Okay, so in this case, let's say maybe this part cools earlier, so this part cools earlier than this part and of the outer surface, and once this starts cooling, it pulls in, tries to pull in material from all direction, and there are considerable forces on the outer surface because of which hot tears happen. So something like that. Okay, and so these are other surface level impurities, the top three that can be commonly seen. So first one is a blowhole. Okay, so the blowhole is directly because either water vapor or air got entrapped into the surface. So as you can see, this is like a surface which is high, which is like a dome type of a surface. So chances are the air will get trapped in here, and there's no vent for the air to move out, right? So because of that, the air gets trapped in and the material cannot flow into that, and because of that you will get these blowholes. Sometimes these blowholes the holes can happen just below the surfaces also, and in a longer or a different kind of a form, and these are called scars. So it will be like a scar on top of your skin, something like that. And similarly you will get blisters, just little bit of air or water vapor that has gone in. Okay, so sometimes you get these kind of scabs where let's say you have air or water vapor from 2 or 3 places which coalesce into a place before the molten material is, or rather after the material is molten. Okay, after the material is slightly in a molten state, it tries to coalesce but it cannot. Okay, so imagine like 2 or 3 bubbles coming together at some places. So these are kind of scabs that are created. Okay, and sometimes what happens is that once you pour the material, because of the turbulence of the molten material, some amount of sand is washed away. Okay, and so you pour in the material, and this is the gate, this is the part where it needs to be filled up. This is the cavity. So because of the turbulence at this end, at this point of where it is entering the whole thing, there's the molten material kind of washes away some of the sand, and this creates like a wash kind of, this kind of creates a problem in the casting. Okay, then there is another form where let's say you have a very long thin part. Okay, And the idea is that you pour from one end, the material needs to travel from one to the other end, okay, to fill up. So what happens is that once you pour in, the molten material also cools down as it travels to the other end of the casting cavity, okay. So when it cools down, sometimes if the the front of the molten material which is flowing, okay, it cools down before it reaches the end, you'll get this kind of casting defect where the material is not fully filled into the cavity, okay, because the flow front has cooled down before it reached the end, and this is called a misrun. And finally, let's say that there's a specific kind of design where instead of the molten material filling from one end only, you have 2 or 3 places where it fills up, okay. And so that means you pour from one end, the gates and all are designed in a manner where the flow kind of enters the cavity in 2 or 3 different places. Now imagine the flow of the material, it flows in, and at some point these 2 flow fronts, okay, this is an important terminology, these 2 flow fronts kind of interact with each other, and at that point, if the molten material is not sufficiently hot, then they'll not entirely merge together, and what will happen is that there'll be like a line which you can see, and this is called a cold shut, okay, or in plastics, in injection molding, it's called a weld line, okay, WELD, weld line, or in case of casting, this is a defect, it's called a cold shut. And cold shuts are a big problem because they are, it's sometimes difficult to see also, and they are a place where chances of failure are much higher, right? It might get broken and so on, okay. So these are some other kind of things. So flash I already explained. So in this case, what happened? The cope and the drag were not fitted together with enough force, with enough clamping force, and because of that, the molten material flowed into these in that thin section between the cope and the drag, and you got a flash. In this case, you made the cope and the drag, but there were some alignment issues when you were casting. So you had the cope and drag, but they shifted, okay, they shifted slightly. So because of that, you got this kind of a mold shift error. And finally, you didn't clean up the molten metal properly, or the sand itself had some impurities which were not compatible with the casted material, okay. So those things get included into the casting, and these are called inclusions. So sometimes they are good, and sometimes it's okay to have them. You can machine it out and all that, but sometimes they are a problem, right? So what you can see on the top is like a scab that is created, okay. This is a scab. Okay, and blowholes, sometimes you will not be able to see if there are blowholes in the casting unless you do some special kind of tests like ultrasonic, X-ray and dye penetration tests, okay. So these are typical tests that are done, and in this part which is cut in 2 halves, you can see that this is a blowhole that is created. So that means there is not enough venting that is happening at this part of the casting. Similarly, there's some amount of blowhole that is there over here. I don't know why that is created. There's some flash that is coming over here. Yeah. So these are the casting defects. In this case, it's showing you a misrun. Think about this part. It is thin and it is large. Okay. I think it is large. And once you pour in the material, most likely the material is poured in from the other side. It flowed in, and it kind of, so cylindrical parts, it's especially a problem. Think about a cylindrical part. You pour in from one end, it fills up like this, and it joins at the other end, right? So if the flow front cools, in this case it did, if the flow cools down and before it fills up the whole thing, you'll get like a misrun. Okay, and this is also somewhat like a misrun. It's not a misrun, but this is like a cold shut, and you have these two places where, so this one shows like a problem after a cold shut. Okay, it's not showing a cold shut. Cold shut are not clearly visible. I mean, you'll see it like a clear line only, but this is a failure that has happened after the cold shut. So the flow front tries to join in, but they could not. Okay. Chaitanya asks, how efficient is casting in terms of high production output? Is it a slow process for making things in large numbers? Well, compared to, let's say, die casting, it is certainly sand cast. Okay, casting is an efficient process. Okay, casting is an umbrella term for several different types of processes. Okay, it is certainly a very efficient process. That means that if you design the production line in a certain way, that means, let's say, one side of the production line is making the cope and the drag, they are transferring it to the others, and the other side they are melting the material, getting ready to cast, and so on. If you design the production line, you can have good production output. Okay, it certainly isn't like injection molding. Okay, we'll not compare it to that. Let's compare it to something like machining. Okay, it's fairly high output considering machining. Okay, it can be done, and things like die casting, it is further high output because you're not dealing with something like a non-temporary mold. Okay, so in sand casting you are dealing with temporary molds, but in die casting you are dealing with permanent molds. Okay, and right, so and what else? Is it slow process for making things in large numbers? It's slower than sand casting is slower than die casting. Let's put it that way. Sand casting is slower than die casting. Die casting is fairly fast, and die casting is slower than injection molding. So if our gold standard for fast production is injection molding, then it is fairly slow, but it is still done quite a lot. In fact, Chaitanya, the parts of the motor that you disassembled, the pump that you disassembled, are made using casting, and so in a typical production line that makes pumps like that, you would produce probably thousands of pumps in a day. So you can imagine it is possible to do something like that. Okay, right, so let's move on. We spoke about this. So now what we will do is let me just go to a point where I think I'll stop. Okay, I want to stop, so I'll stop here. Okay, so let's the very little. So now the second thing that we are going to discuss is something called parting line. Parting lines are very critical in design for castings, in all types of casting, die casting, sand casting, and all. Okay, and in this image you see two different parts. Okay, the first part, it is slightly irregular in shape. Okay, you have this one side at a certain slightly higher level and the other side at a slightly lower level. Okay, it can be casted. It's not a very critical thing to cast. Okay, it does not show the draft angles, but imagine that there are draft angles in this. So this can be casted, but to cast this in a manner which to cast this directly, you would need to have a parting line which is slightly irregular in shape. That means, imagine the cope and the drag. In the cope, you would have some things projecting out. Okay, it's difficult to make something like that. Okay, and if the volume of production is fairly large, then it is very difficult to control something like that. So rather than that, it's better to have like a straight parting line. It's always better to have something like this. Okay, so in this case it's difficult to have a straight parting line because of the irregular shape. You can't even cut it in the middle and expect to have like a straight parting line. Okay, so yeah, so that is one of the design considerations that you should have. Okay, so typically in a formal class, okay, I'll answer Fahim's question. He asks, how can misruns and cold shuts be resolved? Well, uh, so in today's time, typically you don't directly jump into casting once the model is ready. Okay, so the way the process goes is you design something in CAD and you can simulate the whole casting process in a computer, in a software. Okay, it's called computer aided manufacturing, and there are some softwares like ANSYS and I don't know exactly which ones are there, but there are several types of softwares which can help you simulate casting. So generally you simulate these castings. Okay, and when simulating you can clearly see if there are problems of misruns and cold shuts or any kind of other issues. I think things like inclusions and all of that is not clear, which depends solely on the properties of the sand and the molten metal, right? Whatever you can kind of see in the design aspects, you can clearly see the problems that may arise. And cold runs and mixed shuts are the problems of the flow front and the design of the cavity. Okay, and so these can be simulated very easily. So you would simulate it and you would see if there are such problems, and then you would modify the design. So that's the best way to do it. Okay, to avoid to resolve the problems of cold runs and mixed shuts. However, let's say we moved forward, and or rather it's a small scale facility which does not do such kind of CAE work. So you let's say you go into production directly, and then you realized, or rather you do into pilot, and then you realize that there are these problems. So typically the way to do it is you rearrange the flow. Okay, so the places where the cold shuts and misruns are happening, most likely you would try to pour material in such a way that the material reaches there faster, or some extra material is there, or the temperature that is there at that location is not too drastically different. So that's how you would control. So it's a fairly trial and error and experience oriented process if you're not depending on design software. Okay, so I hope that answers your question. Let's see the next one. So that typically in class, what I do is I ask this question: can you make a perfect square in casting? Okay, because we have already discussed about draft angles, and we know that if you want to cast a cube, a perfect cube with 90-degree sides to each other, you will not be able to do it typically standing straight. So you can do it if you have like an irregular parting line. So let's say you orient the cube in a certain way where the parting line is jagged right on this edge, and you can cast the cube easily. You can orient it in a certain other way, and you have at least 2 or 4 sides which are 90-degree, you are assured, but one side you need to machine to make it 90-degree. Sorry. And this one, in this way, if you want to cast a cube, you will always have to give some draft line. So it's possible to move and orient the parts that you design in a manner that will give you the closest to what you want. Okay, so yeah, so that is just an interesting exercise for a class. Right, so this will be our last slide for the day, and we'll talk about some things here, and we'll end with the casting this thing. Right, okay. I had some things to show you also, so I'll show you that, and then we will end. So these are some of the design considerations that you should think about when you are thinking about anything related to that needs to be manufactured with casting or things like forging, injection molding. So these come into play. Okay, the first thing is the minimization of undercut. So in this design, you see that there's this place where there's going to be a hole and there's a lip, right? This small space that is created, no, if the parting line is over here, you will not be able to remove this part, okay, because of an undercut which is created. So so because of this space there will be an undercut, so you will remove this space when you want to design for casting. Okay, similarly these spaces are undercuts. Okay, and if you want something like this, you would need cores to be on the outside of the part. You would need to have, like, let's say this is like a cylindrical cross section part. You would need cores on the outside fitted as rings, right? So it complicates the whole thing. Better remove this, or if you do want these kind of features, you have it through machining of the part. Similarly, the same thing. So basically the manufacturers really dislike the use of cores because it creates a little bit of challenges and whole thing. So better to avoid cores as much as possible. However, if you think that it is absolutely essential for a design, then you can have cores. Okay, but even then you need to consider these facts. Sometimes you would need two cores, okay, to have a certain design. So this one, if you designed it like this, then you need two cores, one which goes like this, one which goes like this, for each of these two undercuts. Rather than that, if I just remove this small part over here, I can make do with one core. Okay, so that's the idea. Similarly, in this, what you had done is, let's say you had this is the top view, this is the side view. In the side view you have this small lip. So this area over here that you see, you need a core to fit in. But if this is just for clamping purposes, then you can redesign the part in a certain way that it it removes the need for a core. Okay, so these are some of the simple design considerations for process. So sorry, let's, okay, I hope you see the images. Okay, so this one was not very clear to you, so this is what it looks like. Okay, yeah, so we will stop here. There are a lot more other things that needs to be discussed in casting. We missed yesterday's class, so we will make up for it some other time. I'll send you the details for that later on, and I will also send you the assignment. Okay, so, or rather, I mean, I'll type you the assignment. I know what the assignment is. I'll show you what the assignment is. Okay, so let me fill up my, right. Okay, so can you see me? I hope you can see. So in one of the previous sessions of this class, so one of the assignments that I gave was, you make a model of a casting of an object. Okay, and what these kids did was something like this. So this is a box, okay, and this is like this is made out of paper. Okay, just paper model, and this shows you the casting setup. So it slides off and all that, but it's not. But it shows you the casting setup. It shows you the cavity. So imagine this is the scope and this is the drag, and you have like a cavity which is made. Okay, can you see? So here this student has tried casting a diamond. So here is the diamond shape. Half of the diamond is on top, half of the diamond is on the bottom, and you see this cavity. This is not required on the on the drag, but this basically is like the riser, and this channel that you see is like the gate. Okay, and here is the hole for the pouring basin. Okay, not here. So this is like the this is like the gate. This is like the gate. This is the place for the riser. This is the place where the sprue meets the gate, the runner. Okay, and this is the drag pattern. Okay, and the drag pattern on top, you have like a pouring basin and a small place which is a vent. Okay, and the vent connects to this. If you can see, I don't know if you can see. Yeah, it shines probably. So this, there's a vent here. So this is exactly how it looks like, right? So it's a very simple kind of a casting setup for, let's say you want to cast a diamond. So you would put these two together, and now if you pour metal, like not on this is paper, right? So if you pour metal, it will flow into that shape and it will take the shape of the diamond. Okay, so that's the idea. So another student did a very interesting one where she did like a cross section view. Okay, so she did it in a thermocol. Okay, so let me first figure out the thing. Right. So I don't know if you can see it. I hope you can see it. Let me get some light and shadow going. So here, this is the cavity that is going to be casted. Okay, and this is the shape of a lamp, of a old lamp, old lantern, right? So that is the shape that is there over here, and it has all these kind of design, features with slightly raised edges. And for all of these places where it's high up, right, she's created these vents. Okay, so these vents that go up to the top and these vents that go up to the top, right? And then you have two places. So this is the pouring basin. So you can see there's a small basin that is here. Okay, and this is the sprue. I think it's a larger sprue because she wanted this to be the riser itself. Okay, and this goes down. There's a small place where it catches the material, and there's the gate, and it flows into the material. It comes to this end and it flows up, and this is the other riser for the model. Okay, so this one kind of is helpful to explain the casting diagram to students. Had you been here, I would have showed you, but yeah, this is all you get right now. Okay, right. So your assignment is to do something similar. Okay, you make a model of a casting setup. Okay, so what you do is you take a familiar object. So you take an object, something that like take a small piece. Okay, and using whatever material is available to you. Okay, you make you can use chart paper, you can use thermocol, you can use whatever material is is available to you, with which you can make. Okay, you can take sunboards or cardboards or whatever. So whatever you take, you ensure that it looks fairly good. I mean, these look good, right? They are clean and all that. So even if you use like Amazon chart paper, you can make it with that, but once you do it, try to paint it so that it looks nice and all that. And what you need to do is, let's say I chose this object. So this is a small object, right? So I want to make a casting diagram of this. Okay, right. And what you do is you take a look at all of this, you really analyze it. Okay, I want to make a casting diagram of just the bottle. Okay, so if there needs to be a cope or a drag, or if there is an undercut, then think about all of those things. Okay, and the first thing that you do is make a simple drawing of it. And what should be the casting diagram look like? Okay, you need to make a drawing in an A4 sheet or whatever, so digitally or whatever. Make the drawing in whatever manner you can easily can. So you make the drawing and you ensure that all the things are in the right places, right? So you are considering all the design, you are thinking about all the design considerations, and you can go through the slides. There are some other things also that are important, right? I will just show you with I'll just show you so that you know, right? So the idea of heat mass, to balance the heat mass. So in this case, let's say this entire thing is the part that you need to cast. The riser needs to be at the place which has a larger heat mass, okay? So that, you know, when whatever is the largest volume in the casting cavity, when that cools down, it cools down more and it will try to pull in material more. So there should be scope for it to pull in material when it cools down. So it's best to keep the riser towards that part, okay? Similarly, so it's very easy to see here. So in this case, this is the part which needs to be casted, and this part is a larger thermal mass than this part. So better to keep the riser this way, right, on the other side. So yeah, and the other thing, so I'll just put this 2 also. So the other thing that you need to consider is that as far as possible, you should always have the casting with a similar wall thickness, okay? And yes, I will answer your question, just hold on, huh? So you have this let's say this kind of T shape you want to cast, right? So if you can see these circular areas, no, these places will have a larger amount of material than the surrounding areas because of the nature of this design, right? So it's better to have a design which has a smooth flow like this rather than a sharp, you know, directional change like this, so that you minimize. So here in this case of Y, you have reduced the sizes of the arms so that the space here, there's not too much difference between this place and the other places because of, so if there's some differences like this, no, you will get some hot tears and you know, cavities that are getting created over here. So if this cannot be avoided at all, then generally you would make a small core which will be inserted over here and you make a hole over there, okay? So these images we will discuss in the next class, okay? And yeah, others we will discuss in the next class. So coming back to the assignment, so you need to make a drawing of whatever part. So I chose this part. I'll make a casting diagram of, okay, I want to cast it. Where is the parting line? Where is the draft angles? And all of these details need to be there in the drawing, okay? And that same drawings model you need to create using whatever, you know, materials are available to you. So you can don't make the model larger than this, let's say, okay? So this is probably, let's say it falls within the size of an A4 sheet, okay? So just take about that much, that's enough. So these 2 things you have to make, and yeah, don't overcomplicate, but whatever things that you have learned till now in this class, if you can try to incorporate those things into that model, no, it'll be very nice, okay? So Ace is asking if you can make a 3D model. Don't make yeah, if you want to make a 3D model to just explain the drawing, instead of sketching, you can make a 3D model, but the physical model you have to make, okay? So that's what so that's about it for the assignment for today. If you want it written down, I'll send it to you in a mail, and the presentation is there. There are lots of other slides in the presentation which I thought we would have covered in yesterday's class, but that's okay. I'll tell you when the other class we are going to do, okay? And yeah, so if you have any questions till now, tell me. If you have anything else, or we can move forward. I mean, like, we can close for today and we'll wait for the next module, or wait for a communication from my side, and we can plan out a class to make here. Yeah, so submissions, right? So when is our next module? Let me just check that. Yeah, I want to see the class timetable. When is the next? When is our? So Niranjan is asking, should we use actual casted? No, you don't need to use actual casted objects. You can use any object. Okay. So the idea is that, I said no, I'm using this kind of an example. So this is a casted. This is not a casted object. It's an ink pot, right? So I can use this, and I'll think that, okay, this I will try to make using casting. So what are the things that I need to do? So that's the idea. Okay. Next class is on 8th October. Is it? Is on 8th October. Let me see. Okay, so we'll follow the same routine. In that case, you try to submit. I'll give you one more day extra. You try to submit on 4th maximum. Okay, don't be later. Don't submit any late than 4th. Okay, 4th of October, so that I have 2 or 3 days to go through your assignments. So both of these assignments you have to submit by 8th. Okay, 1 week from now. Did you guys see the model that I gave you? The 3D model, the Fusion 360 3D model. How many of you checked? Can I just see a hands up? Okay, no problem. If you have not seen the model, I have put the 3D model in the OneNote folder. I can just show you. Right, just let me. Right, so I put it in the OneNote folder in the class resources section. Okay, and you go to class resources, 3D model of machine pencil. This is there. This is the design. You can download, you can view it on your own, and I put in like a video also. So if you want to see, wait, it's playing on the other screen. So yeah, so just showing off. Right, okay, you check this model out to understand how Fusion works, and we can close this thing. So based on this, you'll understand how to do it, right? And okay, yeah, thank you. So that's it for today's class. Thank you so much for joining in, tuning in, and please do your assignments on time. So except for the people who I have specifically given some extra time, please submit everything that is there, and all of the other people who could not submit these assignments earlier, I will check your assignments and I will go through, give you feedback. Okay, thank you so much everyone. Now we will close the live stream, and go and do your work. Okay, thank you so much. Let's see who all are remaining. Only a few people. Okay, thank you guys. Thank you so much. Bye.